Hi, welcome back. So today we will be talking about a very important concept called linearization. Just a little background, we all know all the physical systems are nonlinear to some extent. A true linear system really doesn't exist in, in real world, and we are usually dealing with nonlinear systems. But it is possible, and we'll see today how, to represent these nonlinear systems with some approximation to be a linear version of those. And then we can apply a lot of existing methods and tools that we know for linear system to these real world systems. So to begin, let's look at this pendulum system. It's just a pendulum attached to a massless rod and freely oscillating. If you want to solve the equations of motion for this, we can draw the free body diagram, for instance, like this. There are two forces, one force from the massless rod or the court, and a force of gravity. If I map these forces onto the normal and tangential directions and only focus on the tangential direction to write the rotational equations of motion, I can write J theta double dot, and I'm writing everything about point O, equals sum of all torques about this point O, which in this system only the component of the gravity along the tangential direction has a moment of force in that about that point. So I'm going to write it here, and I'm taking positive direction to be counterclockwise. So this torque is in the negative direction, which is minus mg sine of theta. That's this small force multiplied by the length. Let me call this L. That is the torque, and I know the moment of inertia about that point O is m L squared theta double dot. I'm going to bring this term to the other side, plus mgl sine of theta equals 0, cancelling out some terms and rearranging. I'll have theta double dot plus g over L sine of theta equals 0. So, as you can see, this extremely simple system is in fact a nonlinear system, as is represented by this nonlinear differential equation. It is nonlinear because we have sine of theta. Remember, linear equations are only theta double dot or x double dot or any derivatives, only a function of simple polynomials of theta. And since we have sine of theta here, that makes this system nonlinear. So that's a sad moment that even this system, with its utmost simplicity, is nonlinear, and we cannot use anything we have learned so far, including Laplace transform, and anything we will learn after this, including transfer functions and state space representations. All of the methods that we will learn in this course does not work for this. So now the question is there a way we can somehow approximate this system as a linear one and then try to apply all the methods that we know in this course to the system? So fortunately, the answer is often, not always, yes. And that depends on the degree of nonlinearity. But for many of the systems that we deal with, it is possible to look at a very small neighborhood of the states that we are dealing with, and within those neighborhood the system can be approximated with a linear version of it. So just to maybe visualize it, let me show you this. So this is the sine of theta that I have here, and I'm comparing it with another function, just identity function, f of x equals x. And so as you can see, these two functions are clearly different, especially at these extremas, that the sine starts to go back in the opposite direction, but the function x just keep increasing. But let me start to zoom in. Well, you still see differences. Keep zooming in along the x direction, and as I make this window smaller and smaller, let me do a little bit of that as well, the differences become virtually non-existent. So anywhere between minus 0.2 and 0.2, the error between x and sine of x is very small, and as long as we are working within that range, it is with a very good approximation possible to replace the function sine of x with function x, and that's what we usually do when we are talking about linearization. So I have this. We just saw that, let me write it here, when theta is small, and how small depends on you and how much error you can tolerate. In this case, sine of theta is approximately equal to theta, and I can write this equation as theta double dot plus g over L theta equals 0. Now this is a linear equation, linear ODE, and we can do a lot of stuff with it. And surprisingly, for this condition, we will see at the end of this lecture, it's really not a bad approximation either, and it works even for decently large amounts of theta. It won't be the case depending on how much nonlinearity you have in your system, but as I mentioned, in many of the engineering problems, it is possible with good degree of accuracy and to work with a linearized version of a system, and we can still manage to do a lot of stuff. So what we just did is what is called linearization. Perhaps you can see versions of this when in a lot of contexts, maybe in physics as well, when you assume theta is small, and instead of starting with this, you build that assumption of theta is small into your solution to arrive at a linearized equation. But, well, that works, and sometimes it's even the simpler way to tackle a problem. One of the examples in the textbook nicely shows that. But for this, right now, let's get a little technical and see a very general purpose and generalizable way to linearize any nonlinear equation. And that is, I'm sure many have at least heard, is the topic of Taylor series or Taylor expansion. Series or Taylor expansion. So if we have a function, and this is absolutely any function can be, this is my x, f of x, and it can be anything. So with Taylor expansion, you can approximate your arbitrary function with any level of accuracy that you want by using this form. So your f of x, this is Taylor expansion. So for instance, you want to start and build your approximation about some point x naught. So Taylor expansion about that point is f of x naught This is a very poor approximation because it approximates the entire function as a constant value of f of that point. So we can do better. We can add other terms. F prime of x naught. This is the first derivative of function with respect to x evaluated at x naught. For the sake of completeness, I'm going to write 1 factorial, which equals 1 times x minus x naught. Now we are approximating this function with a line as a function of x, which is better than the constant value, but we can keep going. Second derivative of x evaluated at x naught divided by 2 factorial x minus x naught squared. Now representing this with a quadratic function, and we can keep going to infinity. As you add more and more terms, your function, your approximation, becomes closer and closer to f of x, and the limit of this series as it goes to infinity, truly approximate f of x with zero error basically. And again, maybe to visualize this, let's see. Okay, we are back here. So imagine I have a function, any function. In this case, I'm taking the exponential function f of x equals e to the power x. This is a very nonlinear function. And let's see what happens when we try to do the Taylor expansion. So I'm plotting the function and the approximation, same as these ones. And as I add more and more term, increase the degree of this resulting polynomial, see what happens. So at the 0th order approximation, I'm just taking the value of it and pretend the entire function has the same value. As I increase the order now to a linear approximation, my approximated function is a line that is tangent to the original one at the point of interest. And if I keep adding, making it into a quadratic one, a cubic function, and keep increasing the order, you can see my approximation gets better and better. And in the range of 0 to 5 and approximating thing around 0.3, you can see maybe an 8, or let me go a little higher, see what happens. Maybe a 9th order. at least in this scale that we are seeing it, very well approximate the nonlinear function e to the x. So that is, let me go back to the linear approximation of it. This is what we are interested in the most. Approximating a function within the vicinity of the point of interest with a line. And if maybe I can try to zoom in. Similar to the case we had before up here. Where was it? Here. That the sign of x around x, we see we could approximate it with x, function x. We can also try to zoom in and see that as we get closer and closer, or zoom in and make a narrower view, this becomes a, oops, no, don't go there. Oh, I lost it. Going back, let me zoom again. Oh, don't do this. Don't do this to me. Okay, that's better, hopefully. But you can see, to have a reasonable approximation of e to the x, we have to be closer to the point of interest. Before sign of x, around point 0 was fairly linear itself, and maybe with a range of minus 0.2 to 0.2 we had a good approximation. But e to the x at point 3 is fairly nonlinear, or I would say a lot more nonlinear than sign of x at 0. And to have a good approximation, we have to be much closer to this point. So that is somehow a notion of what is the degree of nonlinearity, that you can sense how close you need to be to represent your function as a line. Okay, going back. So that's what Taylor series is. And maybe as a last bit of intuition and visualization, let me redraw this, maybe a slightly nicer, and see what we are doing. What this really means, this weird looking function, if it's not. So this is my function, f of x. And I'm looking at this point, this is x naught. This is f of x. So what it's doing is taking this value, f of x naught, and then making a line tangent to it. And if we are close enough, this value, which I'm sorry if it's a little small, is going to be almost equal to the actual value of the function, this point, and that, where is it? And this point. And the red one that I'm showing is exactly that, the derivative, which is delta y over delta x multiplied by delta x. So this distance is x minus x naught, and that rise is slope, which is derivative, multiplied by this advancement, x minus x naught. And everything is added to the value of function at that point. So that's what this, the first two terms mean. Additional terms approximate the function instead of with a line. For instance, if it's a quadratic approximation, with a quadratic function that not only the slope is the same, but also the curvature at that point is the same. And you can keep adding and adding, and you make more and more derivatives of the curvature to match at that point. And that leads to better and better approximation until you go to infinity, take this series to infinity, and you fully approximate the entire function. All right, so maybe this is enough space for me to do one quick example to make this whole discussion more concrete. An example. For instance, I have my original function f of x equals sine of x. Now let's try to approximate this around x equals 0. So I'm just going to use the Taylor series expansion. So f of x equals, let me write it again, f at 0, which is sine of 0, which is 0, plus f prime, the first derivative of sine of x, is cosine of x evaluated at 0 divided by 1 times x minus 0 plus the second derivative. The first derivative is cosine, second derivative is minus sine of x, which I'm evaluating at point 0 divided by 2 factorial. Let me put factorial here. X minus x naught squared. Let me add one more term. Derivative of minus sine is minus cosine of x evaluated at 0, 3 factorial x minus x naught cube, and so on. So f of x is 0, 0, plus cosine of 0 is 1 times x, 1 divided by 1 times x. Oh, why do I have x naught? Let me be prettier, make these all 0, 0, 0. So 1 divided by 1 times x is x. Sine of 0 is 0, so that whole term is gone. Minus cosine of 0 over 3 factorial is minus 1 over 6, 1 over 6 x cube and if you keep adding, the next one will be again a sine, will be 0, and the next one will be a fifth order, so this is 1, 3, 5, 7, all the odd exponents remain. 1 over 5 factorial, what is it? What is 5 factorial? I don't know. 120? I don't know. x5, and the next one will be negative, and keep going. So this is the Fourier, the Taylor expansion of function sine of x. And if we only keep the linear terms, so we can say sine of x equals x plus, usually we say higher order term, higher order terms that we often ignore. So sine of x is approximately x around x equals 0. So that is essentially how we can concretely find what function we need to replace this sine of x to arrive at that, other than just searching through infinitely possible functions to see which one best approximate sine of x. So take a moment to think about all of this while I clean the board, and I will be back with a little bit more and we should be done. Okay, welcome back. So we saw that this Taylor series expansion can be used to approximate any function as a line by taking the first two terms, the linear terms. But in practice, this is insufficient because we often have, imagine this function you're trying to approximate is your differential equation that may be a function of positions, velocities, accelerations, time, and many other variables. So in practice, we are often dealing with functions of x, y, z, etc. A function that takes more than one input, and we also need to be able to approximate such function using Taylor series expansion. And we can do that, and it's very easy. Just a little bit more notation, but that's completely doable. If we have this function and we want to approximate around x naught, y naught, z naught, and all other possible variables that are the inputs to the function. We want to take this, approximate it about that operating point. So this is what we can do. So this f of x equals, similar to what we had before, f of x naught, y naught, we evaluate the function at the point of interest, z naught, dot, 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 plus the first derivative of a function multiplied by the distance of our actual point to this reference point. And if you recall from your calculus, if you want to calculate that differential, we can resort to partial derivatives. And for the sake of brevity, I use a notation that is fairly common. I use f sub x evaluated at this x naught, y naught, z naught, dot, 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 divided by 1 factorial x minus x naught. And this, I'm going to write it up here, that f sub x equals partial f partial x. And same for all other directions. So partial derivative of f along y, again evaluated at the point of interest, divided by 1 factorial. The movement or the distance along the y direction. And let me complete this. F z, which is partial derivative of f with respect to z, or z, evaluated at x naught, y naught, z naught, all those points, 1 factorial, z minus z naught. So all of this is the first order approximation, or the linear approximation. And then if we have more variables, we need to add them here. All of these are the linear terms. Plus, now we can work with the second derivative, second order systems and do the second derivative, and the notation people use is f sub xx, which again maybe I write it here. F sub xx equals second derivative, second partial derivative of f both times with respect to x. Again, evaluated at this point. I'm just going to call it x naught, 2 factorial, x minus x naught squared plus fyy evaluated at the same point. This x naught is the shorthand for all those points. Y minus y naught squared plus fzz at this big x naught, 2 factorial z minus z naught squared plus dot dot dot. If you have, I don't know, time and other variables beside x, these are the quadratic terms, and plus all other higher order terms, cubic and fourth order and so on. So it is kind of big, but remember that we often do not need this because we want to linearize the system in the context of this course. So we only care about the first line, or the linear terms. And it is usually the case that these partial derivatives are fairly simple, and we can easily calculate those. So keep this in mind and think of it for a little bit while I clean the board and I come back to solve one example. Actually, no, I have another thing before that. Now that this is on the board, let me show you what this approximation really is in practice. Remember that, let me go back up. Here, when I only had functions of a single variable x, I was approximating the function with a line that was tangent to my original function at the point of interest. In the multi-dimensional version of Taylor expansion, the first order approximation, or the linearized version of the function, is a surface or a plane that is tangent to my function in both directions, and yes, it's tangent to the function. So if I move around my operating point or point of interest, you can see my linear approximation of this function remains tangent to my original surface. Sorry, my laptop is not the fastest and it takes a little to load as I move my slider. But when we talk about linearizing a multi-dimensional surface, we are basically fitting a plane and making it tangent to the surface of the function at the point of interest. So that is this first line doing. Okay, that is that, and now is the time for me to clean the board. I will be back. All right, welcome back. For the last bit, let's solve one example. So I have this nonlinear differential equation, x double dot. The accelerations are velocity terms multiplied by some trigonometry function of x plus some other function of x. So this is not exactly, I just pulled it out of a hat, but this form that the velocity terms multiplied by some sines or cosines of your variable x plus some trigonometric functions of x. This is relatively common in multi-body dynamical systems when you have multi-joint systems, that the damping depends on the configuration of the system and the stiffness also. There is often some terms back here that makes the inertia, the effective inertia, also dependent on the position, usually comes in terms of sines and cosines of x. But regardless, this is just a toy example, and we want to linearize that system about the point that position and velocity is 0. So this does not exactly map onto what we had before, but let me try to simplify this so it fits more or less to the shape of the Taylor expansion that we are comfortable working with, and we can use that. So here I have x double dot. I'm just going to rename some of these to make it easier. X dot is the velocity, so I'm going to call it v cosine of x plus sine of x. And we want to linearize around x equals v equals 0. Let me put some x naught and v naught. And then now this is my f of x and v, which is v cosine of x plus sine of x. Now I have a function. There's a function of two variables, x and v. It is nonlinear. I want to approximate it with a linear approximation about that point. So this is now what we can do. So let's begin. This f of x and v equals, I'm just going to put an approximation sign because I'm not going to go further than the first order terms. Remember, it was the, let me write it down, f of x naught and v naught plus di f di x of this f evaluated at, let me not put it this way, put it slightly, evaluated at x naught and v naught times x minus x naught squared, and I have di f di v evaluated again at x naught v naught times v minus v naught. Oh, why did I put the squared here? And I have skipped the 1 over 1 factorial for brevity. Now we can do this. Evaluating the function at x equals 0, v equals 0. So if x is 0, this term goes. If v equals 0, this term also goes. So this one is 0 plus partial derivative of f. Why did I write it like that? That's what was wrong. Okay. Partial derivative of f with respect to x. So this one becomes cosine of x, assuming v is constant. This one becomes minus v sine of x. So I have minus v sine of x. I'm just going to put x naught and v naught because I'm evaluating around that, plus cosine of x naught. This multiplied by x minus x naught plus. Now this is the first one. The second one, partial derivative of f with respect to v. So assuming x is constant, sine of x is constant, so the derivative will be 0, and cosine of x is constant, just act as a simple constant. I'll have only cosine of v naught times v, let me clean it up, v minus v naught. So and now let's put the numbers. Sine, whenever we have sine of 0 is 0. Also we know v naught is 0. So 0, this is 1. So I only have x minus x naught, which x naught was also 0. So anything from this whole expression becomes x plus cosine of v naught is 1 times v. Wait a second. Am I missing something? No, I'm not missing something. Plus v. Close this. We don't need this. So closing the loop. Now my f approximated around that point through a first order approximation is this. So putting everything back, my x double dot is going to be x plus v, or x dot plus x. So this is a rather lengthy way of coming to a linearized version of the original differential equation. It is the true way to do it. However, there are kind of shortcuts that you can think. If it is, if you think you can know that sine of x approximated about 0, you can write it as simply, let me put it here. So I could do this, x double dot equals, let me start from here, sine of x plus x dot cosine of x. So this one, we already know it's approximately x. X dot, although it is a nonlinear term multiplied by cosine, but we know cosine around x equals 0 is approximately 1. So in many situations, you can do this simple kind of mental calculation to come out with x plus x dot. And if you always forget, sine of x looks like this, right? So it is more or less equal to 1, and cosine is this function. So at 0, it is approximately 1. Sine, cosine. So often you can do simple mental math to linearize your system without going through the whole calculation. But nonetheless, this is, if you are dealing with something that is more complex, this is the way to go. Okay. So let me see, what else do I have? So one last thing before I show you a little bit of results again. One last comment is where do we linearize the system around? So I again here pulled this 0 out of a hat and without telling you what's happening. But it is often the point that is useful to linearize your system about is we linearize about what is called no, not there's a fixed point, or is there another name I have here? No, about a fixed point. What is a fixed point? Fixed point is essentially a working state or configuration that if you leave the system in that state, it remains there. So essentially, if all the x at which, or x naught at which all derivatives x dot, x double dot, 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 dot equals 0. So the system doesn't move. The system doesn't change with time. If you leave it there, it stays there. And this is a very good point to linearize our system about, because we are often very interested in that fixed point itself. It is something that either we want to drive the system to, or if you leave the system, it goes back. If it's a stable system, we'll get to that definition later. But if you leave the system from any state, any configuration, it converges to this fixed point. So that is a very important point of operation of a system, and we often want to linearize to work with the system, with the linearization of the system about that important point. So here in this example, x excuse me, x naught and v naught is a fixed point of it, because if you plug in 0, 0 and 0 here, your second derivative will also be 0, meaning that the system stays there. Nothing changes at that time. This system even has multiple fixed points, because every pi multiplied by a whole number is also a fixed point of this, given that x dot is 0. So this is sine. So all of these, for this example, all of them could be fixed points. And depending on which one of them is our interest, we can linearize around that. It is also possible, and we often do this as well, that I write it, I hope there is a space, let me write it here. We also sometimes linearize around what is called operating point. What it means, so you have a nonlinear system. It could be a multi-body dynamical system, or a robot, or anything like that. And the robot is moving. It has a position and a certain velocity in on its joint. But at any given point, my robot looks like this, and it's moving, so a certain velocity as well. This particular configuration that the robot is at now is also very useful. It's an important point or state of the robot that we often want to linearize about the current state of the system, and we can then use the linearization, for instance, for control. So this is also a common point to linearize the system. We don't just go about and linearize about any arbitrary point, because it's often not useful, and if it's too far from where we are, our linearization is going to be not a good approximation. So, all right, that's that. The last thing I have to show is a little bit of comparison. So maybe going back here before showing you that. Let me try to remember. Okay, so going back to the original pendulum, I'm going to quickly draw it here. I had x double dot plus g over L sine of theta equals 0. This was the nonlinear equation, and the linearized version, x double dot plus g over L theta equals 0. Let's see how different if we simulate the response of these two systems. How do they differ? So we expect them to be different because this is the real system. This is an approximation of the system. But let's see how good that approximation is. And in the plots that I'm showing here, let me make this go to 0. So I'm starting from, if you see here, this is my pendulum, and I'm pulling it to some initial theta and releasing it. That's what this plot is showing. If I leave the theta at 0, both of my linear and nonlinear system tells me that my pendulum is going to stay there forever. Now if I give it a little bit of movement, bring it to 0.1 radians and release it, you see two lines here. Maybe it's not visible. I believe there's a blue one. I should have put the legend. There is a blue one that is the nonlinear system and a red one that is the linearized version. And you can see the responses are very similar, even in long times, about 10 seconds. So if my original angle and the movements are small, I have very good approximation. If I increase the original angle, now my pendulum moves back and forth between minus 0.4 and 0.4 radians. Now you start to see differences, that maybe my linear system is oscillating a little. If I assume the red one is the linear one. No, I think, let me go check the code. How do I check it? Oh, this doesn't show me. Let me do this. So blue one is a nonlinear one, red one is the linear. What? No. Yes, no. Blue one is linear, red one is nonlinear. Okay, that's first one is linear. So blue one is a linear one, and it oscillates a little faster than the nonlinear one. You see it starts to peak a little earlier than the nonlinear brother. Go up. Okay. And if I keep increasing the movement as it becomes larger and larger, you see I lose my validity. And if I keep going, even to 1 radians, which is 50 something degrees, it's a very sizable angle. It's not negligible. You can easily see it, and it's not a small value. At the beginning of the motion, I have decently good approximation. The linear one is a little bit faster, and it shows up more and more as time progresses. But if momentarily and for short periods we only consider the linearized version, still it's a decent approximation. It's not too far off. And let me keep going up and up and up. The error keeps increasing, and I think I have to get to close to around 3, that you see The linear one is still continues to do the sinusoid, but the nonlinear version becomes weird. So around 3, so I have almost flipped the pendulum. 1 pi is 3.1. So at a little less than 180 degrees and let it go, you can see this is really not a good approximation anymore. So even in very short amount of times, the linear and nonlinear one, the linear and nonlinear behaviors are different, and getting closer to 180 degrees, I completely lose accuracy. So the two responses are very different. Let me 0.14, which is still less than pi. So my nonlinear one is upward, and it takes a long time for it to slowly bend and starts oscillating. But the linear version doesn't see that, effect, nonlinear effect of gravity, and immediately it starts to go back towards 0. So okay, this is all I have, and so this concludes basically the mechanical system, modeling of mechanical system. In the next 2 videos, we analyze behaviors of first order and second order systems, and we'll see how we can extend these analyses with more complex and advanced method later on. So until then.